Okay, I'm Ariel Weisbein, this is Damian Saura, and this is a joint research project with Ariel Futoransky. We're going to present a timing attack against database engines, and let me start. Now, database engines are used daily to store huge amounts of data and to access this data efficiently. Web applications use them, and they typically store credit card information, personal data, security numbers, a lot of sensitive information that must be guarded. So this is why attackers target a database and the data they hold. Now, there's been several attacks against databases to compromise the data. For example, typically, an attacker can break into the web server and steal the data. This can be due to insecure configuration, lack of patching, or any problem in the server hosting the database. Also, web applications that use databases in the back end typically have SQL injection vulnerabilities and other vulnerabilities which can be compromised, and attackers can use these vulnerabilities to steal the data. Yet further, some databases that can be reached by users, but these users aren't authenticated, are vulnerable to authentication problems, and an attacker can impersonate a standard user and steal the data, or simply an authenticated user can steal all the data from the database when he's not supposed to do this. So these are all attacks from the past, and we're introducing a new attack where an attacker that is able to make inserts into the tables, but not select operation or steal or access the data, can eventually access the data and steal all the information in the database. So all this talk is going to be about how to do that. Now, let me summarize the main result before I continue with the talk. Consider a populated database with a lot of data. It has many tables, and one of these tables has a sensitive information in one of the columns. And an attacker or a user is able to make inserts into this column. Think of this as, for example, credit cards that an attacker or a user can fill in his own credit card, and by doing this, he can later extract the data. So users can make these insert operations, and also they can time the time it takes for the web application or the database to respond to their insert operation. Then the attacker can succeed in stealing all the data from the database. And the complexity of this attack and the success probability of the attack is based on many parameters that I will describe during this talk. But mainly, I can say that it's the number of bits of the sensitive field times the number of values you want to steal, the attacker wants to steal. So more explicitly, this attack depends on the indexing structure used, B-trees, which is used in most commercial databases. However, we only implemented this attack against MySQL, and I'm going to tell you about our MySQL implementation. So what does this vulnerability imply? What can we say about the problem with indexing sensitive data using B-trees? Well, apparently indexing might be a bad idea in terms of security, and it needs to be researched further to understand how big is this issue, and whether a given implementation, a configuration of a database is problematic or not. But there is a trade-off here between efficiency and security, as it always happens. And also, taking into account the complexity estimate I just told you of, this is only one attack. We are not sure if this attack could be improved. and we do have some evidence that it could be improved. So I'm going to tell you about some numbers and some results that we achieved, but probably one could do better. So I mentioned indexing tables is a bad idea, and let me give you an example of why is this so. Imagine a content management system that has users and passwords in a table, and they are displayed in this way in the web application. From the web browser, you can register, and registering, you type your username and your password. Of course, passwords cannot be seen, and they are written as asterisks, hidden from standard users. However, imagine that both username and passwords are sorted, so that when you click on username or you click on password, they are ordered alphabetically. So let's say that when you click on password, they are reordered alphabetically by the password. Then, for example, here you know that Tom's password is earlier in the dictionary, in the alphabet, than Dick's password. And if you're allowed to add username and passwords, many of these, then you can make a divide and conquer attack, a binary search, and find out any of the passwords in this table. So indexing is problematic. Sorting, is problematic. Now, the attack I'm going to present is different from this, but this should be evidence that some people that think that sorting isn't problematic, they are wrong. So to continue this talk, I will go through database management systems and the indexing structures. I'm going to prove or give evidence that these databases leak information, and then build on the attack. So how does it go? Now, database management systems are applications accessed by either web applications, web servers, or any application that has a database in the backend, or by standard users. They have a persistent storage, they have a hard drive typically that stores all the information, and this needs to be stored efficiently for the web server, the web applications, and users to access this information efficiently. So typically they use the relational model or the SQL standard or variations of this. To summarize this, one could say that data is stored in tables. Each row of the table stands for one record, and all the fields of the record are divided in columns. For example, username, password, or here, name, passport, football team. And these rows are sorted by the values somehow in the database. If they weren't, then searching for the data or making insertions would be very inefficient. And also it should be noticed that you cannot have all this data, huge amounts of data in RAM memory. So it must be stored in the hard drive. And typically what one will do is access chunks of this memory and perform operations over these chunks in the RAM memory. So this is the architecture of a typical database management system. As I mentioned, data is sorted in chunks, which are called page disks. And every time a user performs a query, it goes through all the blocks there. But to summarize this, the user will make a query. This query gets compiled, and it is forwarded to the storage engine, and the storage engine will access only the chunks of memory, the pages that are necessary for performing this operation, and retrieve this data to the execution engine and finally to the user. And it should be understood for this talk that the cost of each of these operations is typically dominated by the access to the hard drive, by writing and reading hard drive. So database management systems try to minimize reading and writing in hard drives. However, by doing this, there are time differences between each of these operations, and we thought that perhaps you can use these timing differences to extract information to the database, from the database. Okay, so a little bit about structure of the database and how data is stored in the hard drive. There are many different implementations of this, but in the end, for every sorted column, you get pair this column with an identifier for the record, maybe a pointer, maybe the data itself. Here you find two examples, the unclustered index and the clustered index up and below. And this is the way the table on the middle is stored. These columns that are sorted are called search keys, or from a search key you can build one of these columns. And what you need to do is sort efficiently these search keys and have a data structure for inserting these and looking up for them efficiently. So one of the ways to do this is with B-trees. A B-tree is an idea that dates from the 70s, and it's basically a balanced tree, meaning that from the root to each leaf there's the same distance, the same length, and there are some design principles which are known, and then different database management systems will implement this differently. For example, each node should be half full, and this rule is almost always obeyed, but the nodes have a full capacity. We will call this the N, the size of each page. And here you see some search keys, 28, 8, 13, 28, 35. And these search keys are paired with the data as I showed in the slide before, like this. These passport numbers stand for the leaves or the values, the search keys in this tree. So here I only put the search key values, but this should be linked to the actual data somehow. Now leaf nodes, the lower nodes, are stored in a linked list somewhere in the hard drive, and you can see how to search for values in here. Now if you want to search for a value, say for 5 in this tree, you start from 28, and then you know that you need to take the left branch, and you get to the node that has 8 and 13, and since 5 is smaller than 8, you go to the left branch again, and you access the node that stores this data. So the way a database management system will work is the search engine will know that it has to access this page, which has the values 1, 4, and 5, and it will send this page to the buffer with all the data accompanying it, so it can be accessed by the user. So inserts are also likewise easy. I'll show you below. The problem is with inserts or deletions that require, for example, deleting or adding one new node. Let's see. Here's some toy examples. Imagine these 2 leaf nodes. I forget about the rest of the tree because it wouldn't fit in the slide. And we will start adding values to these nodes and see what happens. For example, we add 15, and it goes to the left node. And we add 21, it also goes to the left node. 18, 43, and now we add 33. And since it can't fit in this node, and it should be placed in this node because it's a value between 1 and 43, then the node must be split. And it is split in 2 halves that you see printed there, one with the values from 1 to 10, and the other one with 15 to 43. It should be noticed that now these 2 nodes are half full. The node starting with 50 is on the left. I couldn't fit it in the slide, but it's not deleted nor joined with the other values. Simply a new node is created. Of course, this happened with leaf nodes, and you need to make some modifications to the upper level node. Add this value, maybe, as it happens here. Now, it could happen that once you do this, the upper level node is also full, and then you need to do this again. There's nothing very difficult about that, but let's continue with this example. Now, as I mentioned, once the node is filled, it is split in 2, and each node is half full. Now, this insert can be perceived by a user making the inserts because it takes more time. Because once he did this insert, a new node was created, so the database had to write to disk, and some new operations needed to be executed. Now, let's make insertions differently. How can we do to turn this leak or this time difference into an attack? So let's imagine that we know a little bit of information about the node here. The node here, it has some values 3, 6, 7, 9, and 10. But let's imagine that the user or attacker knows that it starts with 3, and that the node on the left, which isn't displayed here, starts with 18 or 17, 20, 25. And we make inserts 11, 12, 13 until 16. And once we get to 16, once we get to 15, the node is full. Once we add a new value, the node must be split. So, from the user or attacker point of view, he knows the value 3 and the values 11, 12, 13, 14, and 15. And he knows there's been a split in this page. He knows that the smallest value is 3 and the biggest value is 5, and that each page should fit 10 values. So he can infer that there are other 4 values between 3 and 11 inside this table. He doesn't know the values by themselves, but he knows in which range they are. They are from 3 to 11. Now, this is very interesting because this could be turned into a binary search by simply establishing one range and guessing if the range contains values or not in the database. You can repeat this iteratively, lowering or dividing the size of the ranges or the intervals you are querying, and doing this you can finally end up guessing the values in the database. Let's see how to do this. So generalizing what I said, as I mentioned, one can establish a range, and making a few intelligent insert operations, knowing a little bit of the earlier configuration of the database, you can guess if this database holds some values in this range. Why? Well, because the attacker or the user knows what's the size of each page, and by inserting values in each of the upper and lower bound of the interval, he can make it split, and once there's a node split, he knows exactly how many values were placed in this node. Also, it should be mentioned that for our attack to work, we require that the keys are primary, meaning that they are not allowed to repeat. So if you try to insert a key that is already in the tree, you will get an error. This is not necessary to carry out the attack, but it's simpler to explain it this way. So if the attacker or the one executing the attack inserts a value over a pre-existent value, then he guesses one of the keys in the tree, one of the keys in the table. That's what we want to do. We want to get precisely that error.
So it does not require primary. He cannot have the user.
No, for the attack, I'm going to explain now. Keys might be primary. They are not allowed to repeat. However, our attack could be generalized, and we made previsions, and we know more or less how to do it. We haven't carried it out, but we have an idea how to do it. But for the rest of the talk, let's assume that keys are primary and they aren't allowed to repeat. So as I mentioned, we want to make this binary search, and it's going to be this way. Imagine the keys in the line as in the upper level, and first we try to decide if the first key in the tree is on the left half, or on the right half of the tree. Once we know it's on the left half, we can divide this in two and guess if it's in the first quarter or in the second quarter. And we continue in this fashion, each time dividing the interval in two and guessing whether there are keys there or not. So what we need, what I will try to build during this talk, is an algorithm that, first, a split detection algorithm. We need to detect splits. This is not evident, and I will show you, at least in MySQL, that you need to do some work. It's not evident how to get to detect splits. And also, one algorithm that, using this split detection algorithm, can tell you whether an interval has keys in its first half or in its second half. So I put here an example to estimate the cost of an attack. Imagine a table holding databases, which are 16 digits decimal value, so it's between 0 and 10 to the 11th minus 1, and that's about 56 binary digits. So assume each page contains about 512 keys, that's 2 to the 9th, and then our attack will need to invoke the binary search procedure approximately 46 times. Why I delete these 10? Well, because once we know in which page the key is, and once this page is smaller in its range than 512 than this page size, then we can search for this by brute force. We need to exhaust only 500 values, which isn't a lot. So let's start with the attack. First, I'm going to explain precisely what scenario we faced. Now, as I mentioned, we are going to execute this attack and estimate and show experiments against MySQL using the InnoDB engine. However, we are confident that our attack can be generalized, since it is only dependent, in principle, in the indexing structure, which are B+trees that are used by other database management systems. However, we only proved the attack against MySQL, and we can only speak for MySQL. So let's start. MySQL, well, you know, it's an open source, very popular database management system used in many web applications, and it allows you to choose from different storage engines. Remember the architecture I showed you earlier? The storing and indexing is done by different storage engines, and one of these, the most popular, is InnoDB. And InnoDB, surprisingly, uses B+trees to index, and also, using this MySQL with InnoDB, we did a clean install of MySQL with InnoDB in a Windows machine, in a Windows XP, populated the database with different sized tables, and tried the attack against this. And I'm going to show you results against these differently sized tables. And the characterization of the attacker is that he was only allowed to make inserts to this column. Finally, about noise, let's assume that we did several experiments. In the first experiment, the attacker was using the same machine as the web server where the database was running. But we proved that you can move to another machine in the same intranet, and one switch away, and the attack will still work. So the attack is robust to noise, but we haven't moved any further. And the web server where the database MySQL was running other processes, so there was some noise involved. And you need to understand that since we are measuring more or less the time the disk takes to make some operations, all the services that are running and using the disk as well, and the CPU take some time and add noise to the attack. So here's one further example. These are some of the experiments we carried. We carried the experiments against the three size tables with one key, 101 keys, and 1001 keys. But the attack scales well, we proved. And we inserted manually one value, this 1013 and 111, and other values uniformly, and we carried out the attack. And here you have the number of inserts made by each of the attacks and the time they took. So more or less, we have this prior estimate for 1400 and 100, and all the attacks took more or less that number of inserts. So the complexity of our attack can be measured maybe by these two values: the time the attack takes and the number of inserts it makes. Now, here all the evidence and all the things I'm telling you are for retrieving one value from the database, but of course you can apply once again this procedure, maybe with a lower complexity, and extract all the other values. So all I am saying is how to extract the smallest value, but you can continue with this and extract the other ones as well. So let's see how the attack works. Something about page splitting with InnoDB. We need to understand how pages are split. Only using the information leak that I mentioned before isn't enough. So we need to understand not only when there's a page split, but also how are the new configurations of each node that is created. So other than following the design principles, InnoDB uses some ad hoc optimizations which need to be understood, and I'm going to explain them for you to carry out the attack. And basically, if inserts are made randomly, uniformly, or following no apparent pattern, then pages are split when they are full, and nodes are split in half. However, if you are making consecutive inserts, then the optimizations will make create nodes and populate them differently. For example, imagine for 1 second that you have one node which has values 1 to, let's say, 512. Then there's no use in splitting this node in two, since there will be no values. You can store no other values between 256, which is the last node on the left half, and the last value on the left half, and 257, which is the first value on the right half. So in that case, it makes sense not to split the node in two, and that's what InnoDB makes. So let's see. I will need to carry out the attack to these 3 cases of node splitting, and these cases there are a few values on the left, and there's a key value I, which we know the attacker knows, and he also knows that there's no value on the right. So the attacker only knows that there's one node which the rightmost, the biggest value is I. Another case is when the same, but when there's only one value to the right, which I call there K1, and the other case is when there are several values, K1, K2. These nodes are not full, and let's try and see what happens if we add values I plus 1, I plus 2, I plus 3 until there is a node split. This is actually how InnoDB works. So in the first case, we add these values. Once we add I plus some value m minus 1, I plus m is when the node split occurs. The node is full, and next a new node is created, and the new node will hold only one value, and that is I plus m. So if you make many consecutive inserts, and that's like more than 15, I believe, a new node is created, and this node has only one value. It's not split in half. The other case, when there's only one value to the right of I, and we add values I plus 1, I plus 2, and let's imagine that we don't insert a value over k, then there's a node split, and the new node to the right will hold two values, I plus m and k, and the node on the right will have one empty place. We'll have room for one more key. Finally, when there are several keys to the right of I, and you add the values, then all the keys but the first one are moved to the new node, and the first key, K1, is left in this node. So let's see how we can use these cases of node split to execute the attack. Now, this is a summary or an outline of sketch of our algorithm. It goes in 3 phases. first a setup phase where we make certain surgically selected inserts in order to prepare the tree for our insertion algorithm. This will only take a few inserts in complexity. This is not what dominates the complexity of the attack, but we need to execute the binary search. We need the configuration I put here in these two nodes, which is we know one value, or the attacker knows one value A. He knows there's no other key in the node but A, and in the key to the right there's the key we are searching for, the value that we want to steal from the database. We don't know which value it is, but we know that there's a node that starts with K. And the next value to the right of K is B, which is also known to the attacker. So the attacker knows A and B, and he knows that in between them there's a key K, which we want to extract. And our setup algorithm does precisely that. It arrives to a stage where you have the tree in this configuration, and K is the first key. And then you can execute the binary search algorithm, which will loop a procedure that at each time halves the size of the interval between A and B. B minus A, it's halved. And also this configuration is maintained. So A will be on the left node, and the right node will have two values, K and B. Well, there might be other values to the right of B, we don't care. And the size between B and the B minus A will be half of what it was before running this procedure. So we will run this procedure until B minus I, which are known to the attacker, are smaller than the size of the page. That's n. For example, in MySQL, in the experiments we made, it was 574. Once you reach to an interval of that size, then we start searching for the key manually. In A plus 1, A plus 2, A plus 3, you make these inserts until you get an error, and this will mean that you have found K. So I'm going to explain now how does the binary search algorithm work. I cannot get into the details of the setup algorithm, but this is explained in the paper, and for this talk, let's suffice that the setup algorithm will only use the cases 1, 2, and 3 I mentioned before. So let's see how the binary search works. This is almost a proof that our algorithm succeeds, and it will help to estimate the complexity of the algorithm. So let's assume that we are in this situation. K is between A and B. A and B are known to the attacker. There are no values between K and B. K is the smallest value in a leaf. And we start inserting A plus B divided by 2, A plus B divided by 2 plus 1, and all the values that divide this algorithm in half. Now, two things can happen, or three things can happen. Either K is to the left of A plus B divided by 2, it might be on the right, or it might be equal. If it's equal, then we've won. We found the key. So let's see what happens if it's smaller or larger. In the event that K is larger than A plus B divided by 2, and we make inserts A plus B divided by 2, plus 1, plus 2, plus 3, and so forth, we will eventually split the node, and the node will be split in this way. This is the case 1 I mentioned before, and if you recall, the new leaf created had only one value, in this case the last value inserted, which is I plus n minus 1, and the leaf on the right remains unchanged. So we are again in the same setting as before. We could take A as I plus n minus 1, the size of the interval is halved, and we can continue executing this. Now, it should be noticed that in this case, inserting A plus 1 until A plus n minus 1, we made exactly n inserts. Now, we are going to use this n, because if K is smaller than A plus B divided by 2, then we are in this situation. K is to the left of I is I plus B divided by 2, and we add values, and we end up in this situation. there's a node on the left that remains unchanged, holding only the value A. The node on the right has the value K, the value I, and other values to the right. But essentially, we're interested in I, K, and A. And also the fact that here we made only n-1 inserts. So the attacker doesn't know anything else, but if the attacker knows when there's a node split, he knows in the earlier case the node was split after making n inserts, and here he knows there was a node split when he added n-1 inserts. So there's a difference here, and he can exploit this difference because this difference will tell him if k is smaller or bigger than a plus b divided by 2. So this is how the binary search algorithm works. If we make n inserts, then we set a to a plus b divided by 2 plus n and run the algorithm again, else we set b to a plus b divided by 2 minus 1. And we can repeat this procedure because we are, each time it finishes, we are in the same configuration as before. So that's it. Each run will require approximately n-1 inserts, and by making these n inserts, the interval containing the keys halved. But in order to do this, to execute it, we need to detect splits. I mentioned split detection is one of the requirements of our algorithm. And split detection is very specific to the configuration and the instantiation of the database you are using. So I'm going to tell you about our experiments and how our split detection algorithm is robust in the sense that it can handle some changes and it will work all the same. So about the noise. In most of the cases, if you measure the time taken by an insert that produces a split and an insert that doesn't produce a split, you can differentiate one from the other. One will take about 2 times the time as the other one. So in the average, you can differentiate node splits, inserts that produce node split from inserts that do not. However, we don't need. We require a little more. We need accuracy to be perfect and detect node splits always. So there are some indistinguishable cases, but we know that speaking about the average, there is a mean value for inserts that do not produce splits, and there's a mean value for inserts that do produce splits. In our case, I believe it was 32 milliseconds for inserts that didn't produce splits and 70-something for inserts that did produce splits. So in the average, they can be differentiated. And we made this experiment I put here before. We inserted consecutive values and distinguished all the values that were bigger than this threshold value. So maybe there was 32, 33, 45, and then one insert took 85 milliseconds. So we stored the order of this insert. And we did this with all the values. And we measured the separation from one insert to the other, from one insert that took a lot of time from another one. Let's say that we take the ith insert, the I plus nth insert, and the I plus 2nth insert, and let's assume that they are all bigger than the threshold value. Then, this is only statistical evidence. We proved in our experiments that if all these values were bigger than the threshold, then with 100% probability, this meant that these inserts were produced by node splits. Because there were other values that took more time than the threshold, and yet they weren't generated by node splits. So here is a sort of a split detection algorithm. Let me explain. Let's say that we get values I plus n, and I plus 2n, and they are all bigger than the threshold value. Then we write this into a table, and we say this is case 1 because node splits took n inserts, and we know that in case 1 of the cases described below, node splits take n inserts. In the other case, they take n minus 1 inserts, so this is case 2. And you can build a table with all the differences in the node splits and compare this against the values you get over the threshold. And in our experiments, it worked to detect the node splits always. So how our split detection algorithm works, you start with a value I, and you make consecutive inserts, and when the algorithm finishes, it will tell you either if the key K is on the left or on the right. Mainly if you're in case 1 or in case 2, case 3, or a combination of the other cases. We need to differentiate case 1 from the other cases. Now, this algorithm, of course, is not deterministic. It will not work always, but it always worked in our experiments. However, we need to mention that sometimes it didn't take 2n inserts, but it took a little more. So maybe there will be a lot of noise, and this I plus n and I plus 2n will not be located at the start of our insertion strategy, but maybe further. So instead of making, let's say, 1,000 inserts to detect one node split, maybe you have to make a few thousand. And the good thing about this is that with absolute probability in our experiments, when the algorithm says it detected a split, then the guess is correct. However, false positives can happen, and the algorithm might take a little more than 3 times n inserts. So now we need to combine the algorithm, the binary search I mentioned before, with the split detection algorithm I just described. And this is easy. We need simply to establish if the key is smaller or bigger than a plus b divided by 2. So if you recall, there was a slide almost like this one, and this was when k was smaller than a plus b divided by 2, and we made n inserts. Now, let's imagine that when inserting I plus n minus 1, we do not detect this node split, and we continue making inserts. Then we're almost in the same case as before, and in terms of nodes and values in the nodes, we're in the same case. This is case 1 described before, and making these insertions, we will have node splits when inserting n values, when inserting 2n values, when inserting 3n values, and so forth. So this can be detected, and simply if you detect 2 or 3 node splits in a row, let's say in I plus 5n, I plus 6n, and I plus 7n, then using this information you can guess there was a node split, and the algorithm is robust and it can handle this. The same conclusion follows, namely if in that event, if you made inserts until I plus 7n, then the tree configuration remains the one we wanted, and you know that the key k is on the right half. Only that instead of making n inserts, you made n 7 times or 5 times n inserts. And as I mentioned here, you need to redefine a as a plus 3n or 5n minus 1, and the binary search algorithm can continue. In the other case, if k is smaller, then we are in this case, and something similar happens. There will be node split at I plus n minus 2, I plus 2n minus 3, and so forth. So detecting 3 of these node splits in a row, it doesn't matter if they are these ones, will allow the attacker to know that he's in the second case and the key's on the left side of the node. Simply taking b equal to I will suffice to continue with the binary search algorithm. So similarly, this split detection algorithm combines with the setup. I didn't describe the setup algorithm, but let it suffice that they can combine. And is this a good efficiency? Well, we say yes, it is, because if you this attack takes exponential in speed to compute a key. And if you compare 3 times the logarithm of n with n, then for high values of n, it's 3 times the logarithm of n is much smaller. And this means that even if we tripled the time our algorithm takes, triple the number of inserts our algorithm takes, the algorithm is still efficient to detect keys. So this ends my description of the algorithm. I don't know if you have any questions, else I will move to future work, countermeasures. Okay. So how can we improve the attack? Well, there's several things we have in mind, and this is ongoing research. We want to keep on working with this. And the first thing we can ask is, can you take this attack outside the laboratory? Is this a real attack, a realistic attack? Well, we believe it is. However, it needs to be researched further. As I mentioned, we tried this attack from a station away, one switch away from the web server hosting the database, but we need to try other configurations. And also, well, split detection isn't very good. We have evidence making different insertion strategies that split detection can be made with fewer inserts. Say, instead of taking n or 3n inserts, we can take 2 or 5 inserts. But in our experiments, the tree configuration broke, and we couldn't continue to execute this. So we need to experiment further with MySQL. And to this, let me mention that we didn't have good documentation to know how B-trees work. So basically, we read the source code and played with MySQL, but there's no description, and we're unaware about the complete behavior of the indexing algorithms. So maybe there are some optimizations hidden that we didn't find, and profiting from these optimizations, we can make the attack much more efficient. And also there's heuristic optimization that can be made, and this we did experiment with. And this is if you know what's the distribution of the values in the range. For example, if you know they are uniformly distributed, or you know that they are all even, or they have some property, and profiting from this property, the attack can be made more efficient. I put here one example, and instead of dividing the interval in 2, you can divide it into any number of pieces, and check in which piece the key is, and this can be used since our split detection algorithm not only tells you that the key is on the left or on the right, but also how many keys are in this interval between A and B. Maybe there are more keys, and we could generalize the algorithm to work with more keys and to attack them all in a same run of the algorithm. Finally, let me continue with this. Can this attack be extrapolated to other database management systems? Well, theoretically it can. Our attack is only dependent on the indexing structure and split detection, and since most of the commercial database management system use B trees or B plus trees, then in principle the attack could be made to work with these other database management systems. However, there's a lot of parameters that need to be taken care of, such as the optimizations that I mentioned, such as caching, journaling, and a lot of other parameters and inner workings of databases, which aren't explained in the B-trees papers of the 70s, nor in the present papers. And all this internal stuff needs to be analyzed very accurately for the attack to work with this. Finally, what can we do to stop this attack or to detect this attack? Can a run of this attack be detected during the attack execution or by reading the logs, making some forensic analysis? Well, a first countermeasure could be don't index data. Then every query will take the same amount of time, and this is very inefficient, and it's unlikely to be implemented, but in some cases it will help to prevent the attack. There's more realistic solutions or countermeasures which might work, and that's, for example, transaction throttling. Say, if in a given implementation a user isn't supposed to add more than 10 inserts or 15 inserts, then this can be blocked, say, from an IDS or from the web application that is hosting from the web application that connects to the database. But in different ways, one can stop certain insertion behaviors. Also, applying some cryptographic blinding techniques or extrapolating the blinding techniques from the cryptography, one could encode somehow the values that are stored in the database, and in this way the values of the search keys cannot be guessed or are muddled up and are more difficult to guess. However, of course, this will imply a penalty in efficiency and might not be wanted. Also, introduce random delays so that two inserts that produce one insert that produces a node split and another one that doesn't cannot be identified. And this has also been done in cryptography, and it worked in realistic applications. And I think that's it. So thank you very much. And if you have any questions, I'll be happy to answer them.
Could you give one or more examples of like a real life situation where you would have thrown what kind of data in the table that you want to get, and then also the situation that you could really insert those keys individually?
Sure. Well, we executed the attack against search keys with different types of values. For example, 64-bit numbers and alphanumeric strings. 32 values, was that? 32 character strings, and the attack worked with both. Actually, if the size of the values held in these columns is bigger, then splits are easier to detect. And about realistic applications, well, in principle, any web application that has a database in the back end and where a user is able to make inserts, for example, to provide your credit card number, could be used for this attack. However, we did not execute the attack experimentally against a web application, but always against a database as users. So even in a database where, for example, to speak of another situation where the attack could be implemented, if one user is allowed to make inserts, let's say in a commercial application that stores economical transactions where each time a seller makes a transaction, he can add the registers of his selling in the database, and he is not allowed to extract data from other operations, then he could execute this attack and make a lot of insertions and steal the data in the database. So, yes.
Because, for instance, let's say I could create users with a password in the database, right? And say that the password is then the index field. So I could start choosing passwords, and then in this way find a certain password in the database, right?
Yes, correct.
But then I still have the problem that I don't know what it's attached to, right, in the database.
You mean you don't know what's the user?
Yeah, I don't find a user with it, right? So I just find a password that represents this database.
Yes, of course.
I just try to replicate
Yeah.
a very cool attack.
Well, yes, you can do the same with the user, or also maybe you can more easily build a dictionary of users than a dictionary of passwords. So maybe the passwords are securely chosen, but of course the usernames are not securely chosen because they aren't supposed to. And once you guess a few passwords, you try them with a dictionary of usernames and.
Or
Yes, of course.
try and make a list of users in the database and try and make a list of passwords and then try and
Yeah.
combination.
Okay, thank you. Any other questions?
It seems like your attack is almost solely dependent on time of execution, and you stated clearly that one of your assumptions was nobody else is on the database. My personal experience is that any kind of database that's going to contain enough information to be a worthwhile target, be that information health information or financial or just plain personal identifiable information, it's going to have many more than just one user at a time. So you might, I would like to know more about your attempts to improve this in a wild web environment where it's a database that's in use, multiple targets, multiple users. I know that Oracle, for example, in some of its data dictionaries on index, provides information about nodes and leaves and things on a given index. So your split detection may want to rely less on time of execution, which is going to be very unreliable very quickly, and more on specific and identifiable characteristics about the index itself.
Mm-hmm.
If you tend to pursue that more, I'd like to know about it.
I see. About the other users, I mentioned that our attack can handle some noise. For example, if the inserts are being made by other users in another, let's say we're attacking one node, and the inserts are being made in other nodes, then this should not prevent our attack to work. In terms of our profiting from the indexing, it will make some noise to the split detection algorithm. And the split detection algorithm in that case will take more time, so it will require more inserts, but it will continue to work. Only that if there are other users using the database, it might take more time or more inserts to concrete the attack. And we did think about using other operations other than inserting and maybe profiting from the complete set of instructions available for making queries to the database. But so far, I can speak only of insert and, of course, updating, which is almost the same, but not other characteristics particular to the indexing. It was a Windows XP.
Windows XP. I know.
Háblale.
In particular, is it going to work? Did you do a multi-core or multi-processor?
No, we didn't. We only tried with one processor, Windows XP. This is MySQL 5. But we are going to be on the boot of Core if from 4 to 6 p.m. If anyone wants to ask something. This is the boot number 11 and 12 here on 4th floor. We can show about the research we did also.
And as I mentioned, we also tried the same server hosting the MySQL and accessing this as a user from another computer. But always the computer running the database was this slow machine. And we did find out that the attack is dependent on the machine. And if you have a very quick hard drive, then you need to make something for the attack to work. For example, I did mention that if the values in the column have a larger size, then splits are easier to detect. So there's always trade-offs between the different parameters in the attack. And timing is not very accurate, so if you get a very quick application, then probably it's going to hide node splits. Also, if you get many optimizations, or you get a load balancer and a web application and many other nodes between the user and the actual database, then this is going to add a lot of noise, and the attack will be easier to implement. Okay, thank you very much. Oh, there's a question there.
I was just going to say, after you make your 14,000 inserts, it's pretty obvious to the user. It's kind of like a one-time shot. You're going to go in there, try to get as many keys out, and then whoever's looking at the database is going to be like, what the hell is this? 14,000 inserts of junk or consecutive credit card numbers, like that.
Yes, of course. But who does that? Who checks logs? And also, once you stole the credit card, then yes, they find out the credit card has been stolen, but the attacker stole the keys already.
Right. Maybe using one of the other operations again.
But if you're using updates instead of inserts to implement the attack, then it will be that easier to detect that someone was messing around with the database. Also, the attacker could erase the entries after executing the exploit or something. They're trying to hide what was going on. Anyway, the research strategy here was to start from more friendly environment for the attack, and then try to raise the level of difficulty and see how the attack behaves. So these are the first results of this attack, and the guys are going to be working on more realistic scenarios.
Okay, thank you very much.